These next two example problems are not included in the slide deck. Usually these problems are ones that I reserve for working in class. And in fact, I would not have worked these problems for the students. I would have them work them. We would walk around and discuss them and make sure that everyone got the correct answer. So I would really prefer it if you take a moment to read through the problem statement and try going through this methodical approach on your own and see how well you do. It may be that you can look at these problems and just figure out what the answer should be, but I want you to try doing it methodically, because if you can start getting the method on your own and do these steps, then when you get to the harder, more complicated problems that it will be coming up soon, you'll be much more successful. So in this first example, we have moist air, which is simply a mixture of dry air and water vapor. And it enters a dehumidifier at the rate of 23.2 kilograms per minute. Liquid water is going to drain out of the dehumidifier at the rate of 0.5 kilograms per minute. We want to determine the mass flow rate of the dry air with its remaining water vapor that will exit the dehumidifier. So take a moment and figure out these various steps. So remember that first we're going to do a basis, then we're going to do a drawing. Next we want to come up with our material table, a degree of freedom analysis. We'll formally write it out, but you could do it just in your head probably. And then we want to solve the equations and then answer the question. So take a moment, pause the video, and make sure that you know how to do that. All right, so the basis. In this case, you could choose any of these, but I set this up so that I use the feed as my basis. So 23.2 kilograms per minute that enter the device. Okay, I find that it is easier to work with the feed as a basis most of the time. Sometimes it's okay to work with a product, but just that was a choice I made. You didn't have to use that particular one. Then we'll do a drawing. So the drawing, I'm going to have my feed, okay, which is my moist air, coming into a dehumidifier. And I'm going to have dried air coming out. And I'm going to have liquid water coming out. Okay, the feed came in at a rate of 23.2 kilograms per minute. The liquid water drains out at 0.5 kilograms per minute. And we want to determine the mass flow rate of the air with its remaining water vapor. Okay, so I don't have any other given information, so I will name this just F. I have a flow rate here and I have a flow rate here. This is going to contain some water vapor and some air. This one will contain some water vapor and some air. That should be an A. That's stream 2. And this one is 100% water. So my material balance table. So remember I do these for my stream. So I have the feed, I have dried air, and I have the liquid. My components are air and water, and then a total. I'm doing these with units of kilograms per minute, and I can choose to break this up any way I want to. So I can do this as X, excuse me, that was not what I meant to write. Okay, kilograms air per kilogram, kilograms water per kilogram. That would mean that I'm using mass fractions to go with my mass flow rate. All right, so I have the feed is 23.2, the dried air is F, and the liquid is 0.5. My air is, I have no idea, XA1 and X water 1. This is XA2 and X water 2, and this is 0 and 1.0. Okay. Now, in this particular case, I've done a lot of extra work on the material balances. I'm not going to have enough information to determine all of these, but just for the sake of completeness and reviewing the method. Now, the degrees of freedom table. Okay, I have one process, which is the dehumidifier. And I have my streams are the feed, the dried air, and the liquid. So I have 3 streams. My unknowns are, well, 1, 2, 3, 4, 5 of them. I'm not listing them this time, but they're right next to us on the table here. My material balances that I could write 2 because I have 2 components. My sum of x's, I have this set and this set. So I have 2. Process specs, other information given, I have 0. And my degrees of freedom, 5 minus 2 minus 2 minus 0 leaves me with 1. So this one is not completely solvable. However, that's all the information they gave us. And remember, I don't really care about this information here. So we'll proceed to solve this based on what I can do and see if that will get me this one unknown here. And this is a very simple one. I'm pretty sure you could have done this on your own without my guidance. Let's write the material balances. Well, my material balances, I could write component or I can write overall, but if I do a total, 23.2 in is F plus 0.5 out. Therefore, F is going to be 22.7, and the units are kilograms per minute. All right, then I can check. Okay, how can I check? Well, in this case, just logic is all I have left to check with because I do not have all of these other pieces of information. If you were to try plugging them in, you would say, oh yes, they all do work, but that's not very satisfying. So we have, in fact, solved this, but we have not solved for all of the possible information because we did not have enough information. We probably needed another process spec to do more. So let's work another. And again, I'm going to ask that you would please take a moment, read the problem statement, try it on your own. Again, I believe that you could do this before you ever walked into the course. Try it using these techniques. So 100 grams of 90% sulfuric acid is to be charged to a batch reactor. So in other words, this is what I need to go into a reactor. Now remember, we're not doing reactors yet, so don't freak out. Okay, I'm going to be making the stuff for the reactor. A waste acid containing 40% acid is available, as well as an unlimited supply of 98% acid. If the waste acid is to be mixed with the 98% acid, how much of each will be required to create this 100 grams of sulfuric acid product? So in this particular case, my basis is 100 grams, okay, of 90% acid, and this is going to be the product for this. Okay, so I'm choosing this as my basis. Next, I want to do a drawing, okay? So in this particular case, I have a mixer, and it's going to create a product that is going to be 100 grams, and it's 90 grams H2SO4 per gram of mixture, 0.90, okay, 90%, okay, and the rest of this is presumed to be water. And what I have is I have two feeds. I have a stream that is my waste acid, and I have a stream that is my strong acid. Okay, the waste acid is 0.4 grams H2SO4 per gram total, and the strong is 0.98 grams H2SO4 per gram total. I have not written in the water. All right, so this is my drawing. Now let's do our degree of freedom table. So I have my streams. My streams are the waste, the strong acid, and the product. I have H2SO4, and I'll do mass fractions, and H2O, mass fraction. And then I have the totals on each of these, which is going to be in just grams, right? This is a batch, so it's not a flow rate. Okay, so H2SO4, in the waste acid, it's 0.4 and 0.6. And the strong, it's 0.98 and 0.02. And my product is to be 0.90 and 0.10. The total amount, I don't know. I named this one W, this one S, and this one I know I need to get 100. So how about degrees of freedom? Okay, degrees of freedom. I have one unit, it's the mixer. I have my streams, okay, which are the waste stream, the strong acid stream, and the product stream. I have my unknowns, which are W and S, so there are two of them. I have my sum of X equations. Well, I'm not putting these in the normal order. I have 0 of those, right? They're all known. I have my material balances. I have 2 components. And then I have process specs, which is anything else in the problem statement that I haven't used yet, and I have 0 of those. So my degrees of freedom, 2 minus 2 is 0. This one's ready to be solved. Okay, so let's do the solution. Well, my material balances I can write out. W plus S equals 100, right? The total in equals the total out, or the total at the beginning equals the total at the end. And then I can write material balances on the H2SO4 or the water. So 0.4 W plus 0.98 S is going to be 0.9 times 100. And 0.6 W plus 0.02 S equals 10. And I can solve any 2 of these for the other. So it kind of doesn't really make a whole lot of difference here which one you do, but solve your little system of unknowns, and I came up with 0 equals 13.8 grams of the waste acid. S is 86.2 grams. Check it, whichever, if say I use these two, check it in this one. to be sure, okay? And then once you check, then you are able to go through and make sure that everything really did work, okay? And so the answer was how much of each will be required, and I have my solution. So these two problems, again, there may be some easier ways to work them. We are trying to develop a technique that will work even on the really hard problems.